Okay, so we are finishing up section 5.3. And so today we're going to be talking about the second part of the fundamental theorem of calculus, which is just called the fundamental theorem of calculus part 2. And this is the part that you're going to use more often, and that is probably more useful. And we'll see that we can use this to compute definite integrals in a way that is not so tedious and long as what we've been doing. And so what we're going to do is try to think about this or approach this idea from the point of view of a particle with a position function s of t right here and a velocity v of t. And we know that velocity is the derivative of position, so we're using our intuition in this case to come up with the statement of this fundamental theorem. Okay, so we'll consider a certain interval of time. So consider an interval of time AB, right? T stands for time. And what we know from section 5.1 is that when we integrate from A to B the velocity of the particle, whatever value we get out of that definite integral, it will tell us the distance traveled. Right? Or really it will tell us the displacement, so it's not because we're using signed area instead of total area. But in any case, that's just a technicality. We also know, so we're sort of putting together three facts, and we'll just put them all together, and that will give us the fundamental theorem of calculus. So we know this first thing, that the integral gives us the distance traveled. We also know that velocity is the derivative of position, right? We mentioned that. And then we can reinterpret this to say that S is an antiderivative of V. So V is the derivative of S is the antiderivative of V, right? Okay, and the third thing is that another way of computing the distance traveled, if we have the position function, is just to take the difference of the position at the end point B and the position at the beginning point, but also an end point of an interval A. So I'll write that down. So we can also compute the distance traveled by just using the position function. By using S of t, and that would be S of b minus S of a. So just evaluating at the endpoints and taking the difference, right? And so with the fundamental theorem of calculus, part 2, I'll write it out, says, it will be more general and we'll state it in a second, but in the context of this problem, it just says that these two things that we said both tell us the distance traveled, here and here, they're equal, right? So that shouldn't be so surprising if we say that they give us the same value, right? So the integral from a to b of v of t dt is equal to S of b minus S of a, right? So this was the idea for this particular problem, but it does hold for more general functions. So if f is a continuous function, Here f is going to take the place of v in our statement above. So if f is continuous on the interval a to b, and capital F is any antiderivative. So remember that antiderivatives are not unique. So we can just pick one. Then, well, let's see, of f. So capital F is an antiderivative of f. Just to be super clear what that means that the derivative of capital F is equal to f. Then what we can say is that the integral from a to b of f of x dx is equal to that antiderivative capital F evaluated at b minus the antiderivative evaluated at a, right? Okay, so this is the statement for a general function f, continuous function that is. Okay, so just a couple of statements or remarks about this theorem. First of all, it does say that we can use any antiderivative of f, right? So remember that if we have an antiderivative, I'm just going to abbreviate antideriv. So if capital F is an antiderivative of little f, then we can define a new function g that's f of x plus some constant c is also an antiderivative. And that's the reason why we always have to add that plus c when we're asked to find the most general antiderivative of a certain function. So what happens when, say f, capital F is in its most basic form, right? And we were to instead use g to compute the definite integral. So if we were to just apply this formula up here, but using g instead of f, since they're both antiderivatives, we could use either one. That means that this should be equal to g of b minus g of a, right? And so we have a formula for g. We'll just use that right here. So that would be f of b plus c, that's the first part, minus f of a plus c, right? And so this simplifies to just f of b minus f of a. And I wrote this out just to point out that if you were to use, so maybe it's a little bit easier to see with an example. So say your function was 2x, then one antiderivative is x squared and another one is x squared plus 1. It's better to use the simpler one, as in this one that doesn't have a plus constant on it, because what always happens when you do this computation is the constants will cancel. So we had a plus c and a plus c, they end up canceling because we distribute this negative, right? So we get minus f of a minus c, the constants cancel, and so in practice we always use the simplest antiderivative, which is just not going to have plus any constant at all. So let me write this out. So in practice, use the simplest antiderivative. Okay. And so we will do some examples in a second. The other thing I wanted to point out, and unfortunately there's not room right here to, I'll just use this, I'll mark this off. I don't think we'll need that much room for these problems. Actually, I might need more than that. So I'll write this right here. So this is actually pretty important because we've had this new notation, these integral signs and things, and it's important to keep in mind what these actually mean, because there's going to be some notation that looks very similar, but they represent very different things. So first of all, we had the indefinite integral, which we defined in section 5.1. This is the most general antiderivative, right? And this it looks like the integral of f of x dx. There's no bounds on the top and the bottom, it's just bare. That's an indefinite integral. Okay. What this thing is right here, this represents a family of functions. And so the reason is that we get, remembering that if we have an antiderivative, we add that plus c to account for all possible constants. That gives us an entire family of different functions. So there will be a different one for each value of c. And there are infinitely many values that c could be. So we get an entire family, a very, very large family of functions, right? Okay, so that would be the first thing. The second would be the definite integral. So this looks similar, but this is where we have bounds on the top and the bottom of the integral. And what this gives us is a number. So remember that this is the area under, the signed area under the curve, whatever f is. And this is, so this is a number, right? And then lastly, so we have the indefinite integral, the definite integral, and then the that function that appears in the fundamental theorem of calculus part 1. So that's that thing we usually use g of x to denote this. It's the integral from a to x, where we have a variable in the top bound of f of t dt, right? This is a function. Maybe I should do this in the same color we've been doing the other ones in. So this is a function, right? So like we did in the in-class work, evaluating this function at different values, for every input it gives you an output. So it really is a function. And just so you know, this appears in the fundamental theorem of calculus part 1. Right? Okay. So this is good to keep in mind, that these things all look similar, right? There are slight differences, but they represent really different things. So be careful. You check and make sure, you know, you either have numbers in your definite integral, or if you have a variable, then it represents a function. And then if you have no bounds, that represents a family of functions, and it's the most general antiderivative. Okay, so let's go ahead and do some of these examples. So what we want to do is first determine an antiderivative for the function that's inside of the integral, right? So here we're trying to use the fundamental theorem of calculus, which right up here, right? And we want to use it to evaluate these definite integrals. And so first we figure out an antiderivative. Like I was saying, we want to use the most basic one. So the most basic antiderivative of e to the x is e to the x, right? And so by the fundamental theorem of calculus, to evaluate this definite integral, we just evaluate the antiderivative. I know it's the same as the function in this particular case, but we take the antiderivative, evaluate it at the endpoints. So one way of writing this is to use a bar, so a line. Make sure it's large enough so that it doesn't look like a 1 or something like that. And then we'll write the bounds sort of at the top and bottom, right? And so that's going to tell us that we first evaluate this function at 5, so the top bound, and then we evaluate it at the bottom bound, e to the 0. Okay, and so when we use this notation to denote this, it's really convenient because we'll be doing a lot of computations like this. Just note that the bar comes after the thing that you want to evaluate at those bounds. So the bounds are on the integral sign in front of the function when it's the definite integral, and then once you find your antiderivative, you write that, and then you write a bar, and then you put your bounds on the bar, if that makes sense. And then we can simplify this just a little bit, so e to the 0 is just 1. Okay, so let's go ahead and do the next problem. So we can do this in the same way. So the first step is to find an antiderivative. An antiderivative of x cubed would be 1/4 x to the 4th. And then an antiderivative of negative 6x, we can just keep the negative 6 out front. That's a constant multiple. So we leave that there, and then the antiderivative, simplest antiderivative of x is 1/2 x squared. And then we write our bar, put our bounds on, and we'll use those in a second to evaluate. So I'm just going to do a quick simplification. So we would get 3x squared. And then we go ahead and plug in 3 to this equation. So that means that, okay, I'll try to write a little bit smaller so I don't run out of room. 3 to the 4th minus 3 times 3 squared. That's the first part, right? Then we write minus, and then we have to plug in 0, so it would be 0 to the 4th. In fact, this whole thing will be 0, but we'll write it out. 3 times 0 squared, right? Okay, and then we can simplify a bit. So 3 to the 4th is 81 over 4, and then this is 27. And then if you find a common denominator, you should get negative 27 over 4. Okay, so continuing on, we do basically, we want to do the same thing in C, but first we should multiply out this thing so that we can find the antiderivative. So that's the best way of approaching this problem. So this is from -1 to 1. We would get u squared plus 2u minus 3u, so minus u minus 6 du, right? And then the next step would be to find an antiderivative. Maybe I'll write this a little bit farther along. So an antiderivative of u squared would be 1/3 u cubed. Antiderivative of u would be 1/2 u squared, and then this is just a constant. Antiderivative of that will be negative 6u. Okay, so that's our antiderivative. We're going to evaluate it at these endpoints. So it'll be -1 and 1. And then it's just a matter of plugging them in. And so remember, you always start with the top one. You plug that one in first, and then the bottom one. Okay, so that will be 1/3, but this is just 1, so minus 1/2 minus 6, and then minus, this will be negative 1/3 minus 1/2 plus 6. And one thing I will point out is that it's really easy to forget to, so make sure you put parentheses around the second one, especially, because it's easy to forget, and then there will always be a negative here. If you don't distribute it, you might get make that mistake, and so get the wrong answer there. But this should be, I'm not going to work this out, but you can double check. Just find a common denominator, combine everything together, and you should get negative 34/3. Okay, and lastly, we have this example. Notice that the dx is on top of the fraction here. So it says dx over x. This is just a more compact way of writing the integral from 2 to 4 of 1 over x dx. And I'm just showing you this because you will see it in the textbook. They like to write it with the dx on top, I guess to save space. So just keep an eye out for that. It's not that the dx is missing, they just write it in the numerator. We usually don't do this unless it's just a 1 in the numerator, or maybe just a constant, just so you know. Okay, well, 1 over x, an antiderivative of that is natural log of absolute value of x, right? And so this is a simple antiderivative. It just basically comes from that not family, but the table of antiderivatives that we had from before. And so then it's just a matter of evaluating natural log of 4. The absolute value of 4 is 4, so I'll skip writing the absolute value, minus the natural log of 2. We can actually simplify this using our log laws. It's not necessary, but we can. So we can rewrite this as natural log of 4 over 2, so this is just natural log of 2. And that is our answer. So see that we were able to do 4 integrals, and definitely things that we were not able to compute before, and we were able to do them much quicker than what we'd been doing before. Okay, so that is all for the lectures for this class. Make sure you answer the very last comprehension check question, and then we will do some work in class.